Hi, my name is Jim Larimore. I'm the Chief Officer for Equity and Learning at Riiid Labs, an AI and education startup. And I'm joined today by Thomas and Tiffany, who are going to share a bit more information about an exciting data set idea that they have proposed. So Thomas and Tiffany, I'm wondering if one or both of you might say a little bit more about your idea for the data set and what you think the world would be able to learn if it's created.
Sure. So I'm Thomas Price, an assistant professor at NC State University, and our idea is to create a large labeled data set of programming data that comes from classrooms, K-20 classrooms, so including primary and secondary education, and to develop a set of benchmarks and challenges that can facilitate research to improve computing education using that data set. So the data set, which we can talk a bit about what already exists, but the idea is that it would include students' work on programming problems in classroom settings. So that could be anything from a science class in middle school that's trying to incorporate a bit of computational thinking into their curriculum, a little bit of programming, all the way up to a university level advanced course on programming, what we think of as a computer science major. The goal here would be to facilitate the comparison of different data-driven approaches for example, doing prediction tasks, doing analytics tasks on these data sets, and to have a shared data, set of authentic classroom data on which we could compare the performance of these various algorithms.
Terrific. And why is now the right time to advance this particular area of work? And has anything like this been attempted before?
Well, it's the right time to do this work now, particularly because there's a huge increase in the need for computer science education. And actually, we're getting ramped up in the access to computer science education across the United States and around the world. More and more places are looking to increase opportunities for computer science education, which means that there's more data. There are more classes being offered. For example, in 2015, there were 500,000 unfilled computer science jobs and only 60,000 people graduating in computer science. So states and countries have been putting in efforts and money to educate more people in computer science, train more teachers to prepare students. But that means there's also data sets. But that means there's also an urgent need for more methods to support more learning of computer science for more people. And if we can build machine learned models on data sets from students learning to program, then we can build automated supports for students while they're learning. Because one thing we're seeing is I personally work on teacher professional development for computer science education, and teachers can't do all the support that's needed to learn programming, right? So when the students are generating programs, they all can do the solutions in many different ways. It's not like lockstep in a math class. All the students can come up with algorithms, and many of them can be correct at the same time. And it's really difficult for a teacher to provide really good real-time feedback for that. But the more we can do to do machine learning on those data sets, then the more we can do to automate support for those.
Okay, well, that's terrific. It's very compelling, Tiffany. And what I would add to this is I've been doing some reading on the side just recently about the number of people who've been displaced from the workforce who are now either in online programs or certificate programs offered by community colleges, where computer science is one of the fields that people are really kind of flocking to, looking for great learning opportunities. So it seems like you're onto something that is very, very timely. Thomas, you were about to add?
Yeah, I was going to build on that to say not only is the need great, also the opportunity is great right now. So we're seeing a surge in machine learning approaches for analyzing program code. A lot of that work is coming out of, for example, the software engineering community. And we're seeing deep learning approaches that take in a large amount of data, tens of thousands of snapshots of program code, and are able to make predictions with very high accuracy. And the challenge with applying that to educational data right now is that most classrooms are maybe 100 students, maybe 200 students if it's a large one. And without aggregating the data across classrooms and contexts, it's very hard to test these approaches in educational environments. And so it may be that we have made some great advances and can make even greater advances in, for example, predicting when students are struggling, or selecting the right type of intervention to improve a student's learning automatically, adapting to their needs. But in order to evaluate some of these new algorithms, we also need to look at data sets that are larger than the ones currently publicly available.
I think there's also, I'm sorry, I think there's also some key advances that have been made recently. So, you know, in the AI and education community, there have been researchers like Thomas and myself and many others that have been working on algorithms to process programming data and standardize it, which I think Thomas will speak to a little bit more. But those advances mean now is the right time to get more data and to actually test those algorithms on benchmarks and be able to do comparisons.
Okay, well, that's great. And Tiffany, I think you may be reading my mind, because what I was going to ask is that you've highlighted the importance of the value of this particular work, the timeliness of it, and some of the promise that is there. But I'm wondering if the two of you wouldn't mind explaining or saying a little bit about some of the obstacles or barriers or challenges that you see in trying to gather this kind of data at scale.
Yeah. So some of the challenges are that right now, every class uses a slightly different learning setup, or at least many classes do. And so one of the challenges is standardizing the way in which we, so first collecting the data in the first place, and second, standardizing the way in which we collect it. So there has also been some progress made in that area. I should say that recently, under the organization of a group called CS Splice, a group of computing educators has come together, those who also work in data analysis, to define a shared format. So now there is at least a proposed standardized logging format. That's some work that I've been a part of. So that if we're collecting data from the Java programming language and a traditional programming integrated development environment, like you might see in a professional environment, we could collect data from that, and it would look the same, or at least similar in format, to data we're collecting from, let's say, a block-based programming environment designed for novices, trying to think about how to standardize the way we represent that so that we can apply some of the algorithms we develop more broadly. So one of the, so what I am alluding to there in terms of challenges is not only collecting data in a way that's standardized, but also in a way that allows us to share and compare algorithms or analysis methods. So if I create an approach, so let's say for predicting whether or not a student will struggle on an assignment based on their current program, and you do the same thing, the only way to know whether we're improving on the state of the art is if those two approaches can be compared on a similar data set, or even across data sets. And to do that, we need some standardization.
Now, and let me ask you a couple quick follow-up questions on that. Then one is that with the data currently being gathered, it sounds like it's gathered in individual classes or classrooms by individual instructors. And I'm wondering if you can say anything about generating a level of collaboration or a more collective approach in what right now is a fragmented type of environmental setting.
Yeah, absolutely. So the good news is that there's been a lot of effort recently to organize the community of both computing education researchers and AI and educational data mining researchers to bring them together to have these conversations. I've been part of one effort to do that. I mentioned CS Splice, and another would be the CS EDM workshops. These are trying to bring together computer science educators and educational data miners to think about what this can look like. Right now, you're right, the efforts are fragmented, but we're building that community. And there do exist some tools, for example, the PSLC data shop, which has recently expanded into LearnSphere. We can put some more information about that in the slide. These are central repositories for educational data, and they do include quite a bit of computer science or programming data. But one of the challenges is that there are sort of unique representational challenges to representing programming data. And so one possible future direction would be to think about what would a shared repository of programming data look like that is specific to the needs of programming data?
That's great. Well, thanks, Thomas. And could you maybe say a word or two about the degree to which student privacy is an issue that you all have wrestled with or potentially resolved?
Yeah, I'd love to say resolved. It's certainly not that simple. I will say that some of these organizations that already collect student data in larger repositories have put a lot of thought into this. For example, having staff that validate and collect IRB approval, institutional review board approval, for any data sets that come into their repository, and also sort of informally collecting, verifying that the people using this data are using it for valid research purposes. That said, programming data presents a challenge because it is possible for students to include personally identifiable information in their program code. And so I know that different researchers have approached this different ways. For example, stripping out comments where it might be more likely that students are to put that information. And right now, I'd say that the approach has been somewhat ad hoc. So I think your question highlights a direction for future progress in standardizing approaches to protecting student privacy when sharing program code, because it is authored by the student. It's not like a multiple choice question. It does have that potential to share personally identifiable information.
Okay, terrific. That was very helpful. And what's an example of future work that you think could be built on this data, and who is likely to be most impacted by the work?
So I'll take that one. Future work that can build on this data, as I alluded to before, is machine learned algorithms that could provide feedback to students while they're writing programs. One thing we're seeing in our research work is that students, when faced with a programming environment, they often don't know what to do at first. So if we could have really good data sets where we've gotten good machine learned algorithms that can identify, what has been done for a problem in the past, we can then make recommendations for students to build something. Or we could do things like detect what they're trying to do. Oh, are you trying to make an array? Here's a suggested programming format, or here's an example of how that has been done before. If we can learn from sets of data from prior students doing similar things, then we can provide examples, and we could also figure out ways of standardizing how those examples should look and how to remove personally identifiable information from those, or things that are irrelevant to the algorithm that you're trying to construct, for example. So sometimes in the middle of code, students might change what color a display is, but that's not necessary for an example for another student to look at. So we do want to have high quality labeled data from across classrooms. So for example, like labeling where arrays might be constructed, and whether or not an array is sort of like, if you're doing an array to doing an algorithm to fill an array, is it filling a whole table, or is it filling like the top diagonal part or the bottom diagonal, or just the diagonal, or is it every other element? That sort of thing would be really nice to know. And then if we can have labeled data with sub-goals, we could then also do things like help students break down a task into parts, or detect whether they have broken down a task into pretty good parts, and also analyze their programs and kind of give them feedback, like how good is this program? We could also, importantly, these are all alluding to the potential of generalizing results and algorithms across problems. For example, we would like to be able to take in a student program and give some feedback about how well does a student know some certain concept, like, are they effective at constructing conditionals? Are they effective at constructing loops? Are they effective at making conditions for, stopping conditions for things? All those different kinds of things are important. And then if we could get those, we could actually say, take student programs to assess knowledge, and then we wouldn't have to have a separate assessment after that. And we could also build on that. And we could also adapt exercises to students and have them do more challenging things so they can learn more quickly, right? So if I could figure out what you do know, or what you're effective, like the types of sub-goals you're capable of constructing within a program, I could have you do more complex ones, or have you start composing them together. I'm thinking of all these from the student perspective, but from the machine learning perspective, then we could also take programs and detect what kinds of things they do. And this is not easy to do right now. It's not easy to do on code made by professionals. And then when you look at code made by learners, they make mistakes, right? So if we're good at getting a pattern from good programs, what are we going to do with not good programs? And how do we get patterns of those? And how do we kind of say, all right, this is a decent program, but what would make it really good? And how can I promote students to do that, but also kind of detect things in a way, like group things together, like all these are trying to make arrays, even though, and some of them are really good at it and some of them are not so good.
Yep, that's great.
Oh,
go ahead.
I was just going to build on that to say, if you're a machine learning researcher, you might think about program code as being a form of natural language. It's got a syntactic structure, it's got patterns that frequently recur and semantic meaning, but it's also got open-ended structure and different people construct it in different ways. And so all the ways in which natural language processing has furthered our ability to synthesize and understand the way that humans communicate, there's that equal potential for understanding and communicating what students are trying to do, what they've succeeded at doing, what they're struggling to do, in a way that would allow a system to support that student with real understanding and real adaptivity in the classroom setting.
I think another really interesting thing here is that program data is hierarchical. And if you think about like writing and natural language processing, you know, that's sort of sequential. But so there's some hierarchical structure in programs that might actually, making advances in analyzing programs also might allow us to make advances in natural language processing where we could actually detect hierarchical structures and apply machine learning and come up with new algorithms that take advantage of that. Because I know there are some techniques to take, you know, essays and writing and turn it into a hierarchical structure. And if you had good algorithms that worked in one domain, they might apply in the other.
Yeah, well, that's great. Well, this is a very exciting idea. And I want to thank you both for working on it and the other colleagues who've worked with you on this. Are there any final thoughts or comments that you'd like to share today?
I think we've touched on it. We'll try and include some resources if you're interested in anything we've said in the slides.
I do want to mention that there's an issue about, I think one reason why we don't have a lot of collaboration in the past is that because a lot of us see programming as a creative act, we want students to be creative when they're making things, and that's part of the challenge, like why it's difficult to do machine learning on this. But maybe we don't have as much collaboration because you know, professors and instructors don't want data sets sitting out there of solutions of problems that they've been giving in their classes, or having students all turn in the same thing. They want them to construct their own thing. So I think there's actually a lot of interesting issues with you know, detecting whether or not things are similar, and sometimes that being good and sometimes it's not being great. So there's a lot of really interesting potential here. And I also think it would be really fun to also generate more interesting problems, right? So even though we don't want people to cheat, we do want people to sort of do interesting things that combine different algorithms and approaches in their programs.
Yeah, well, that's great. Well, Thomas and Tiffany, thank you very much for your time today and for the deeply thoughtful approach that you're taking to this work. It's really exciting to hear from you both. And I also like to thank the audience for listening in with us today. And as Thomas has mentioned, more information is going to be posted online after the session for people who'd like to know more about the work that you're doing. So thank you very, very much.
Yes, thank you, Jim.
Thanks for having us.